this lesson called Related Rates is going to take us back to having to implicit differentiate. Remember that one? Okay, so let's practice from last unit. If we derive an x term, okay, so this is 2x, and I'm going to go very technical here. If we derived the x, we attach a dx over dx, meaning we derived x with respect to x. Then the next term is going to be 3y squared. And on that, we derived y with respect to x. So everything we're doing, we're relating it to the x variable. And then the derivative of 10 is just 0. So we didn't write that at all. And we just abbreviated this with just a y prime. That's what we did. And then we solved, right? So it would isolate y prime equals negative 2x, because I'd have to move and divide. Okay, so that's still fresh in our brains. Okay, so we're going to do problems now, word problems that involve us having to do that. Okay, I would like you to implicit differentiate this equation for me, please. Go ahead and give me dx over dx and give me dy over dy. Attach those as well. Oh. I'm going to have to go back a step here. So this is what we did before. We differentiated everything with respect to the x variable. And now we're actually going to differentiate everything with respect to time. So I'm going to just change this bottom here. So instead of differentiating everything based on the x, we're going to differentiate it based on the time. So this really means the rate of x changing with respect to time. How is x changing with respect to time? That's what these are meaning. And this one is obviously, how is y changing with respect to time? Okay, so now we can plug in and we're going to solve. You are given that the change of x with respect to time is 2. So I'm going to plug that in to replace. When the x value is 1. So I'm going to plug that in. So there's my two substitutions. When x is 1 and the change of x is 2. We're going to be finding dy over dt. So I'm going to just leave that as letters for now because that's what we're solving for. I don't have anything to replace y with, but I need something because I can't, it's not my variable. This is my variable. Anybody know what to do? How can I get a y? I can get a y. Plug it into the top. So I know x is 1. So 4 times 1 squared plus 3 times y cubed. Okay. So I am going to need to plug the x value into the original equation to get the original y, right? That's the point of it, getting the original. How did my algebra go? Did anybody get 2 out of that? 2 cubed? Okay, so now I can plug that in. Okay, go ahead, do your math. You're just going to solve. So there's the answer for how is y changing with respect to the time. Okay, so we're going to do the same thing here. All right, so deriving. So to derive a v would just be a variable, so just a 1, and then attach that you derived the variable with respect to time. Okay, deriving this is the front coefficient and the exponent. What happens when you times that front by that exponent? What would happen timesing the front by the exponent there? The 3's would just be canceled, right? So 4 pi r to the 1 lower. You see what I did there? Front times top. Front times top, just made that. 1 lower. And then we need to attach that we derived that variable r with respect to time. Okay, so here's the problem. A snowball is melting. So that's the sphere, right? A snowball is a sphere, a circular object is melting. The volume is decreasing at a rate. The volume is decreasing at a rate of 1 centimeter cubed per minute. So that will get replaced with our rate of volume. How is volume changing with respect to time? -1, because it's decreasing, right? 4 pi. What is the rate of the radius decreasing when the radius is 5 centimeters? So I'm going to plug 5 in for the r, and then it says what is the rate of the radius decreasing. So that's my variable. Okay, so I'm just going to do this. This is 25 times 4, so that's 100 pi. So that's what I'm typing into my calculator. Make sure you put brackets on 100 times pi. So think about your units. I'm going to expect you to put units on this. This is what our radius is changing by. So if the volume is decreasing by that, what's the radius shrinking by? Can you visualize what's happening in a word problem? That's how much our volume or our radius is going down. Okay, a man walks 1.5 meters per second in an easterly direction. So I'm going to start from there and a man walks 1.5 meters per second easterly. And then a woman is walking 2 meters per second in a northerly direction. How is the rate between the two of them? Of their distance between each other, how is that distance rate changing? Exactly 1 minute later. So this triangle is representing my rates. I also need to think about my distance on each one. So 1 minute has passed. If you are walking 1.5 meters per second, how much meters did you go in 1 minute? Can you figure that out?
90 meters.
Yeah. 90 meters, what did you do? Multiplied it by 60 to represent 1 minute, right? So then if I'm multiplying this by 60, that should be 120, right? So I need you to get me this third side. Which is 150 meters, right? Okay, I'm going to start with a formula. So our formula is going to be a squared plus b squared equals c squared. And now I'm going to derive that formula. So the derivative would go 2a, and then I would attach the change of a with respect to time. Every time I derive a variable, I'm going to do that. Plus 2b, the change of b with respect to time, equals 2c, the change of c with respect to time. Okay, let's call A and B. So I'm going to go with the north side as my A and the east side is my B. And then I'm going to plug everything in. Don't forget we're trying to solve for, that's what we're trying to solve for, right? The change of this rate. Okay, so 2a is 120 plugged in there. That's what I'm getting there. And how was a changing with respect to time? That's the rate of 2. Plus 2 times b is 90, the distance of 90. How is b changing with respect to time? That distance of b is changing by 1.5. 2 times c, which is 150, and then that's the variable I'm trying to figure out. Okay, you can probably type this all in at one stage. And I ended up getting 2.5 meters per second is what the distance between them is changing by. Okay, some of you, I don't know if you would have noticed, well, couldn't we have just done that here? Yes, it would have worked out, but we need practice at doing this because it's not always going to work out that way. Okay, so here's a different example of how you can just do that. Okay, a ladder is slipping away from a building. So you have a ladder against a building, and the ladder is slipping away like that. Does that make sense? It's going to fall soon. The ladder is 1.7 meters long. It is slipping away at a rate of 1 meter per minute is the rate of it slipping away. At what rate is the top of the ladder sliding down? I'm trying to solve for that rate. Because, right, as this goes that way, this would be coming down. Does that make sense as a ladder? When it is exactly 0.8 meters away from the building. Okay, we are going to do a Pythagorean theorem to get the distance on that. So make sure you have kind of, it's almost like you have two triangles, right? You have a distance triangle and a rate triangle. So I'd have to use this distance and this distance. So 1.7 squared minus 0.8 squared is my Pythagorean theorem. Because you can only do Pythagorean with distances, right? And then I got a distance of 1.5 meters as a height. That would be the height of the ladder right now. Okay, so give me a squared plus b squared equals c squared to start off. Can you derive it? It's the exact derivative as the top there. Okay, I don't care what you want to call A or B. Let's just go, the wall side is A. So 2 times 1.5 times the unknown variable, because that's what I'm trying to figure out. I'm trying to figure out that rate, the wall side. We're going to plug the B stuff, the ground stuff in for the B. So 2 times the distance of 0.8 times 1 . 2 times 1.7 is the C length, the ladder length. What do you plug in for the ladder? The change of the ladder length. 0. The ladder is not elongating or shrinking, right? So you end up with a 0 over there. Does that make sense? The ladder is just not changing, the length of the ladder. Versus in the last question, the distance between the people keeps growing, but the ladder length doesn't change. Okay, so this is 3. And that's 1.6. So I got negative 0.533 meters per second. And does it make sense why that answer is negative? Because it's sliding down the wall. That's what it's doing, right?
Wouldn't it be meters per minute?
Per minute. Yes. Thank you. Same as that. Meters per minute. Yep. I don't have that very often. It's always meters per second. That's why it's just in my head here. Okay, number 5 is a cone-shaped bin. So you're filling it up with grain. I'm going to draw my farming operation here. How about that? So filling up a bin with grain. And the bin is cone-shaped, so I need to get you the volume of a cone, which I didn't do. One-third pi r squared h. Can you write that down before I flip my screen? 1/3 pi r squared h. Okay, on this question we're going to have difficulties because we have too many variables going on, and this would be a product law, right? Because you have 2 variables in there. Okay, so we're not going to do that. We're going to try to do some kind of substitution. So the cone building is filling up at a rate of this. So this is the rate which is filling up. So that, I'm just going to write over that dV over dt, because that's the change of the volume, right? The height of the building is 10. I'm going to write that on the side. The radius is 4. Find the rate at which the height is increasing when the cone is filled up to a height of 5. Okay, so this is what I know about the bin, and I'm trying to find the rate at which the height. So I'm trying to figure out dH over dt. Okay, because I'm trying to figure out the change of height, I cannot have r's in my equation. Okay, so r, I need to make a replacement for r. Can you use this and get me a conversion? R is equal to what compared to the height? R is 4/10 of the height. Does Does that make sense? If I did it the other way around, height would be 2.5 times the r, right? This is 4/10 of what the height is. Okay, now I'm going to replace that. This is just a substitution. Good? Just a substitution. Okay, so 1/3 pi. So 4 squared is 16 over 100 h squared. Okay, so I just squared it there. Now I'm going to put the fractions together. So this would be 16 over 300. 16 over 300 pi. And then h cubed. Is that good? Did I simplify it good? 16, 300 pi, and there's h cubed. Okay, now we're going to derive that. So dv over dt, if I derive the variable v, I need you to think about front times the top. What happens there? 16 over 300 pi times a 3. Your 3's would cancel like that, right? So you'd get 16 pi over 100, h squared, one less degree. Then once you've derived something with h, you have to attach okay, so that's the derivative. Okay. So the grain was filling up 7 cubic meters per minute, so that's the change of volume with respect to time. Find the rate at which the height is increasing. So find dH over dt, figure that out, when the cone has filled up to a height of 5. So that goes into the h position. Okay? Okay, there you go. See the change of the height at this spot. How much is the height increasing in the cone at that spot? Oh, it's another meters per minute. So the height is changing at a rate of 0.557 meters per minute when the volume is changing by 7. Okay? Do you understand in a cone that your rates are going to be completely different because of your shape, right? A cylinder would increase at a constant rate because of the shape, but a cone, think about your cone, right? The shape of that's the volumes are going to be, the rates are changing, so.